1, adelante.
Muy buenas tardes a todos. Les doy la más cordial bienvenida a la conferencia Colmatación, Causas, Evaluación, Control y Remediación que nos impartirá el Dr. Russell Martin. Mientras se conectan más personas, les comento que al finalizar la presentación del doctor se abrirá un espacio para preguntas y respuestas, por lo que los invitamos a escribirlas preferiblemente en inglés a través del chat que tenemos activado tanto en la transmisión de YouTube como en la de Facebook. A continuación, le cedo la palabra a la maestra Adriana Palma para que nos comparta la semblanza de nuestro ponente. Adelante, le escuchamos.
Muy buenas tardes a todos, muchas gracias por acompañarnos. El doctor Martin Russell tiene más de 35 años de experiencia y es reconocido como uno de los principales expertos técnicos a nivel mundial en el campo de la recarga de acuíferos gestionados. MAR, como lo conocemos por sus siglas en inglés. El doctor Russell ha desarrollado con éxito más de 55 proyectos de MAR ASR, que es Aquifer Storage Recovery, en Australia, Nueva Zelanda y el sudeste de Asia para el gobierno local, la industria y la minería. Posee una experiencia práctica considerable en la investigación, análisis de costos, diseño y operación de estos sistemas. Actualmente, el doctor Russell lidera el grupo de trabajo de la Asociación Internacional de Hidrogeólogos sobre los problemas específicos de colmatación y técnicas de remediación durante la recarga gestionada de acuíferos. Ha impartido muchos talleres tanto como para operadores locales como en foros internacionales y sobre investigación, diseño y operación de recarga gestionada. Le damos la más cordial bienvenida al doctor. Martin, thank you so much. We are going to listen to your conference. Thanks.
Thank you, Adriana, and thank you for that nice introduction. And unfortunately, after 3 or 4 visits to Mexico, my Spanish still hasn't improved much. So thanks for that introduction, and just bear with me while I present in English. Clogging during managed aquifer recharge, just some of the technical considerations and applications that we need to think about when we're dealing with a managed aquifer recharge scheme. So what I want to do, and I hope everyone can see the screen, in terms of the presentation outline, just a bit of an introduction, why clogging is important, what are some of the clogging processes that we need to consider, and some of the bore constructions. The second part will be the evaluation of the clogging risk. Now, clogging risks, we talk about bore construction, making sure we can characterise the receiving aquifer properly, characterising water quality and some geochemistry elements. Identifying and managing clogging, system design and identifying clogging during operations, and steps for remediation once clogging occurs, and then finally just a bit of a summary of what we've been through. And why is that changing my slide? Right, for the introduction, why is understanding clogging important? Basically, clogging can cause impaired recharge capacity and restricts the volume of water that infiltrates or can be injected to the target aquifer. Severe clogging basically in infiltration basins or injection bores may need to be replaced, and it's the biggest risk to the successful operation of any managed aquifer recharge system. And what I should have mentioned is that most of this topic will be on clogging in recharge bores. Clogging in infiltration basins is a whole topic of its own. Now, clogging will happen. We can be sure of that during the life cycle of a managed aquifer recharge project. But the good thing is clogging actually can be managed. There's a variety of different types of clogging, and I just want to step through each one of those in particular. So physical clogging, one of the least appreciated mechanisms of physical clogging is velocity-induced damage, and that's migration of the small interstitial fines that occupy the pore spaces within a sand aquifer or another type of aquifer. And under certain flow regimes and high velocity, these fines can actually break off and become mobilised and flow through the aquifer system. Now, whilst it's not a problem perhaps while injection is occurring, when injection actually stops, these fines tend to sink to the bottom of the pores, and then when you remobilise injection, they mobilise as a clump and then end up being blocked in the small pore spaces, resulting in clogging. It's probably one of the more difficult mechanisms to remediate, but we can actually place put measures in place to actually control that a little bit better, and I'll talk about that as in section 3. Mud invasion, again, probably underrated in terms of a clogging mechanism. Now, muds are designed to bridge the pores and form a filter cake during drilling and keep the hole open and stable. But it's critical that they're actually removed prior to developing the well, and there's different mechanisms to remove them, and if your mud weights and your mud viscosity are not correct when you're drilling a hole using mud chemicals, then they can actually invade out into the pore spaces, several meters or more, particularly if you have a very permeable formation. This is just an example of mud invasion and incorrect, I suppose, development of a bore. We can see in this upper left-hand photo that the mud cake or the filter cake is still completely caking the screen of the well. This middle slide shows a nice clean screen, and that's what we should be looking at in side view after the bore has been developed. Geochemical reactions actually result in chemical clogging, which is one of the third mechanisms that we experience or can experience in a managed aquifer recharge project. Typically, it's precipitation of minerals like iron, aluminium, calcium carbonate. Generally, it occurs through ion exchange, ion absorption, a pH imbalance, oxygen reduction, and formation of insoluble scales. pH is one of the critical elements that we look to control during a managed aquifer recharge operation, because it can actually help prevent some of these chemical precipitation reactions occurring. Mechanical clogging, that basically includes entrained air and gas binding, and that can be either through introduced oxygen in the source water, or even from nitrogen or methane from microbiological activity that might be occurring in the borehole. Hydraulic loading is typically another one. If you operate the scheme with excessive pressures and you have an open hole construction, you can actually result in formation failure or perhaps even aquitard collapse, again, which will cause clogging and reduce the injection efficiency. Biological clogging, mostly generated by small microbes that typically inhabit the aquifer. So we can have bacterial entrainment and growth within the aquifer, especially if there is a food source available for bacteria like iron bacteria or sulfate reducing bacteria. Algae growth and accumulation of biological flocks, that's mainly associated with infiltration basins and is a slightly different concern compared to wellbores. Some of the biogeochemical processes are influenced by chemical type, recharge water source, the temperature, the redox state and oxygen concentration in the groundwater and in the surface water. Native groundwater microorganisms, they're actually great for helping improve groundwater quality and achieving some of the water quality improvements, but they can also result in clogging. The aquifer geochemistry and the presence of co-substrate, dissolved organic carbon. So we might have high organic carbons within the aquifer matrix material. It provides a food source for some of these bacteria like iron bacteria or in particular sulfate reducing bacteria. Now, one mechanism of treating them, we can look at using chemicals such as chlorine or something similar. but then that potentially may introduce another problem in the result of disinfection byproducts that then need to be managed. So again, we need to think about how we might manage and treat these microorganisms. This is just an example of where a change in redox potential, and it is from a couple of a case study in a site in Australia, whereby we have a bore construction in a screened interval of around about 20 metres, and then the bottom part of the bore is basically a sump to capture any fine material or anything like that that moves through the screen. So we can see we've got a low redox potential that's reasonably well oxygenated in the groundwater that's passing through the screened zone, but we have this dead zone in the bottom part of the bore. When that occurs, it's not uncommon to have both iron bacteria, which likes the aerobic conditions, and sulfate reducing bacteria that inhabits these dead zones, whereby it's more anoxic and the conditions are more, and there's less oxygen available. So it's quite possible to have both species inhabiting a bore. Again, the example on the right-hand side really shows the screened interval deep in the aquifer, nice through flow, keeping the system reasonably active, and the upper part of the bore, which is not receiving any flow, could induce the colonisation by sulfate reducing bacteria. And this is particularly relevant where the bores might be shut in for periods of time, or they may be inactive for a period of time, either between the point at which they are first constructed versus the point at which injection first begins to occur. And I'll just highlight that a little bit later on through the talk. These are just some of the oxidation and reduction processes that occur. They're often microbiologically mediated, and groundwater microorganisms gain energy for growth and maintenance. So we can have organic carbon, sulfur and sulfide, iron, ammonia and nitrate hydrogen all lead to oxidation type processes. Reduction, if we've got oxygen present, it provides a opportunity for organisms to take it up, and therefore we go into a slight reducing environment. Nitrate and nitrite, manganese, iron again, sulfate, carbon dioxide, all of these things combine to change the redox state within the groundwater system that we're trying to target, and can result in clogging issues. So evaluation of the clogging risk. I just want to go through aquifer characterisation and why that's important to evaluate the clogging risk. The source and receiving water characterisation is absolutely critical. Some of the geochemistry elements and bore design and construction, because there's a couple of different ways that we can manage clogging. We can either manage it through engineering design, and that's our bore constructions and additional treatment processes, or we can actually manage it through operational activities. So why is it important to characterise our aquifer, especially if we're looking at clogging? What we need to think about is, and often we don't think about it early enough in the cycle of a managed aquifer recharge scheme, because clogging generally occurs when we get to the operational phase, so it's not something that we think about up front, but it's absolutely important that we consider clogging right at the outset of our investigations into the feasibility of a managed aquifer recharge project. If we're looking at an aquifer that has high salinity and we're trying to recharge fresh water into it, we need to think about our recovery efficiency, and that will influence our construction of our bores, our wellfield layouts, all of these sorts of things, which in turn are required to look at where we might get clogging. We typically have variable aquifer properties across a production bore wellfield that results in preferential flow due to anisotropy. We can have different injection rates between different bores, and therefore the methods of clogging or clogging remediation are likely to be different for each bore. So we need to consider these sorts of activities and how it will change across a wellfield. the fate and behaviour of the aquifer microbiology and any introduced pathogens can be quite different between bores. So it'll mean that there might be different remediation approaches applied for different bores within a single well field. So some of the methods that we can actually use to characterise the aquifer, geophysical logging, there's lots of different types, but the idea of doing geophysical logging is it's important to understand zones where the completion is to occur, especially in complex aquifer systems where there may be interbedded lignitic zones, where you have lignite in an aquifer. It's a ideal food source for microbiological organisms such as sulfate reducing bacteria, and therefore in some cases it may be best to actually blank these zones off, and you might have multiple screened zones within the aquifer, but then additional blank zones which are screening these lignitic zones out. The other thing is that lignite can fret quite freely in an aquifer when it's introduced to a different source of water, and therefore result in clogging issues as well. So that's another reason for making sure that we really understand the intervals within which we might have fracture zones or where we might have different mineralogy across the aquifer system. Flow testing over defined aquifer intervals leads to better aquifer definition and how the injected water may behave. It's important to do X-ray diffraction and XRF and scanning electron microscopy to look at what sort of interstitial clay materials we might have that are lining those pore throats, because that may determine that we have to limit the rates of injection so that we don't mobilise these fines and create problems. Certain clays are highly reactive to fresh water. Illites and smectites, for example, are very reactive. Swelling clays like montmorillonite, if they're introduced to fresh water, immediately swell up, and that'll cause clogging. Although speaking with David Pine a year or so ago, he was telling me that they have successfully injected fresh water into a aquifer that contains a high percentage of montmorillonite clays or swelling clays, and so through treatment of the source water and chemical balancing, it is possible to recharge into very difficult aquifers. Cation exchange capacity, again, that's another method that we can use in the laboratory on fresh core cuttings to help us determine just what the reactivity of the clays within the aquifer are to the potential source waters that we're actually going to be introducing. So a high cation exchange capacity means that you've got highly reactive clays, and therefore it'll need, appropriate management measures would need to be put into place to actually manage those potential clays and potential clay swelling that may lead to clogging. If you're doing cation exchange capacity tests, you need to be reviewed in conjunction with the scanning electron microscopy works and X-ray diffraction. And it also needs to be reviewed based on the percentage of clays within the actual sample. Core studies, triaxial testing also can help us to do the understand and characterise the reservoir, the aquifer better, and look at the potential risk of anisotropy, and how we might then go about designing our well field to optimise both recovery and look at optimising the options for managing clogging. I should stress that you don't need to do all of these sorts of tests if you're characterising an aquifer. It is very much site specific when you do these sorts of tests. This is just giving an example of the types of testing that can be done. Column studies is another good method to assess the clogging potential, both of using aquifer material and various types of source water. Very useful because it's a very cost-effective means of testing the aquifer matrix and testing whether or not there's likely to be any geochemical reactions between the aquifer matrix and the source water that might lead to clogging, and or it's looking at options to chemically treat the source water to prevent some of those clogging reactions happening. Just note that there are some issues with using column studies, and that it's difficult to always repack the columns the same as what you might get in the aquifer situation. And quite often I notice that a lot of the column experiments are not actually done using a control. They'll use different core matrices or rock and soil samples and everything in the column, but it's also useful to have a control such as glass beads to obviously manage or just compare the different treatment processes, and that just gives you better confidence in the changes in chemistry that might be occurring due to aquifer matrix reactions or source water quality reactions. Any of the fluids that you use within the column experiments should potentially be degassed, and again, that seems to be one of the things that's overlooked in column experiments. Try and remove as much of the oxygen as you can, because you don't really want to be introducing additional problems that may not be apparent in the actual physical field and at the site. Aquifer discharge tests, again, pretty much everybody understands, I hope, what aquifer discharge tests are. They're the pumping tests we conduct. We can either do a step drawdown test or a constant rate discharge test. What we want to understand is the area that's influenced by pumping, but in particular, what the pumping test does is provide a baseline for aquifer capability against which the various cycles of infiltration, injection and recovery can actually be measured. This provides us an assessment of how effective the scheme is operating, and or if we're actually seeing any clogging that might be occurring. So it's absolutely critical to do, as a minimum, a step drawdown test in the proposed injection bores in order to provide that baseline measurement. And it also means that it gives us a measurement against which we can test the effectiveness of any remediation strategies that we might put in place or might have undertaken on the bore, to make sure that we've got something back to pretty well close to the original conditions before we even started injecting, and it gives us a measure of how effective our remediation strategies have been. Injection, residence and recovery trials. There's various debates about whether these should be and how long they should be done. They're expensive, but they're pretty critical to understanding how the aquifer will respond. And ideally, if we're looking at a larger well field, it helps us just understand what the spacing might be between bores, what some of those issues might be in relation to clogging, and how we might need to manage it. So they provide an indication of what your injection head buildup might be, what your safe operating pressure will be, and those potential clogging issues that we might see in the field, such as precipitation. These injection and recovery trials certainly provide a lot more confidence in the results of numerical modelling, because we can actually calibrate the numerical models to the field trial results, and therefore we can get a better feeling of how we might go ahead and develop our field, our full-scale injection scheme. And basically, the field trials assist in working out whether or not we need to put in other engineering options, such as additional mechanical treatment of our source waters prior to injection, or whether or not we can just manage it through manage clogging through operational activities. Source and receiving water quality for MAR. It's critical to understand the characteristics of both the source water that we're proposing to inject and the receiving groundwater. Some of the critical elements include turbidity, pH, total organic carbon, heavy metals, any microbiological elements within the source water, and depending on what the source of the source water is, emerging contaminants, things like PFAS, which is a big common one. If it's treated wastewater, personal care products and endocrine and pharmaceutical products maybe become an issue and may require additional treatment to remove. The receiving groundwater, the big thing we need to understand there, heavy metals, in particular iron, aluminium and manganese, are the main three that may precipitate. Carbonate if we've got if we're dealing in a limestone aquifer. What's our redox conditions within the groundwater system? What's our dissolved oxygen, the salinity, pH of the groundwater system, and organic carbon? pH differences between source and receiving groundwater are probably one of the primary activities that facilitate clogging and mineral precipitation. Turbidity. Obviously, we want our source water as clean as we can possibly get it to prevent the introduction of interstitial fines. It's not, even if you have sort of suspended solids of around about sort of 5 to 10 milligrams per litre, and you inject it sort of 20 litres per second, you're always putting something in the order of 10 to 15 kilograms of suspended material in the aquifer. So it doesn't take very long to actually clog the aquifer. So you can do simple testing like membrane filtration index testing of the source water to work out what sort of quality and what sort of target suspended solid levels that you might need to achieve in the source water prior to injection, and that will inform you whether activities or treatment mechanisms like wetlands or passive treatment mechanisms like wetlands can achieve those targets, or whether or not you might have to introduce some additional mechanical treatment and filtration methods to actually achieve that source water quality that you need to prevent clogging in the bore. pH, variations in pH, basically, as I mentioned, they result in the formation of scales, carbonate, sulfides, gypsum, etc. Complex iron, pH can cause iron to precipitate out, especially elevated pHs. You can balance pH and keep it below 7, in that sort of 6 to 7 range, to prevent things like iron precipitation, which then the iron precipitation becomes a feed source for iron bacteria. Chemical precipitation, where the ambient groundwater has a low pH and is oversaturated with aluminum oxyhydroxide, that'll also create precipitation. So understanding the mineralogy of the aquifer matrix, and does it have a high concentration of aluminum within it, is important, because if you introduce a low pH water, you will end up with the precipitation of aluminium. This is just a quick example of pH and conductivity downhole. The blue shaded areas are basically the screened interval, and that's the active zone of the formation. In this particular instance, the background salinity of the groundwater is 30,000, so equivalent to seawater, and basically that's what we're recharging into. So we did want to understand the aquifer profile, and we typically have fresher groundwater. As we're looking at the conductivity profile, we typically have a zone of fresher water sitting on top of more saline groundwater, so 30,000 at the top, 35,000 milligrams per litre at the bottom. Within the same aquifer, a little bit further away, we've got considerably fresher groundwater, basically sitting on top of the aquifer. So this is a complex aquifer system with fresh groundwater lenses, but with salinity stratification in it. So we're seeing a significant decrease in the pH profile of the groundwater as we move from the fresh zone into the more hypersaline zones. Total organic carbon. High total organic carbon basically induces clogging because it provides a feed source for microbiological activity. High sulfate is generally a result of organic carbon, and then that can provides a feed source for sulfate reducing bacteria. Sulfate reducing bacteria produce H2S, which can corrode steel and metal casings and other associated unwanted issues. Hydrogen sulfide gas is that rotten egg gas. It's only in very small concentrations you can smell it. In high concentrations it can actually be lethal, and by high concentrations I mean in excess of 30 parts per billion. Generally you can smell it at sort of less than 5 parts per billion. It's that horrible rotten egg gas that you might see or smell when you take the cap off a bore that's been sitting idle for a period of time. Organic carbon removal by microbiological activity basically accelerates the clogging process on infiltration basins, and it can also accelerate the clogging process in bores because sulfate reducing bacteria actually produce quite a slimy residual waste, and that slimy waste will just basically coat the insides of the screens or can coat the formations. Some of the geochemistry. The question we need to ask ourselves is, will reactions occur that lead to clogging? Typically the answer is yes. Groundwater's been there for a long time. It's typically in equilibrium with its surrounding aquifer matrix. What we end up doing is introducing a completely new sort of source of water. So there's this desire to reach a new equilibrium between the groundwater, the source water that we've introduced, and the aquifer matrix. Stormwater, if that's the origin of the source water, it'll have different pre-treatment requirements compared to treated wastewater. The aquifer storage zone is certainly not inert, and therefore there's lots of biogeochemical processes that are likely to occur. So basically we can expect geochemical processes during a managed aquifer recharge scheme. So that's what we want to try and manage against because we want to avoid the clogging. Reactions that are likely to affect water quality, mineral dissolution and precipitation, the ion exchange and the redox reactions we've already been through. The significance of these reactions will vary both in space and time, depending on the physical porosity and permeability of the water and the geochemical and heterogeneity within the aquifer. Source water quality, particularly if you're dealing with stormwater, is highly variable through a season, and therefore different times, different flows and different reactions can occur over time. We operated several schemes quite successfully for a period of sort of 5 or 6 years. Then we had a really dry winter. When the next year came, and very hot, dry summers, our natural surface soils have a high aluminium content. When the next recharge season came around, we were seeing lots of re-injection water with very high pHs, typically 8 and above. And when we injected those into the bores, we were experiencing a lot more ion precipitation and a lot more issues around clogging as a result of that change in I suppose, source water conditions. So what information do we need to assess the risk of geochemical process? We need to understand our recovered water quality. We need to understand the source water quality and the native groundwater quality and any variability within the storage zone. Like I said, in that particular example I gave before, where we have fresher water salinity stratification through the aquifer and quite a different pH between the upper part of the aquifer and the lower part of the aquifer. We need to understand the mineralogy. We need to understand the quality of the groundwater in the storage zone and how that might change during managed aquifer recharge. Best way to do all of this is through running hydrogeochemical models such as Freak, looking at the saturation index and looking at where you may have an issue with oversaturation of things like iron. It's also important to look at the different iron species, iron 2, iron 3 and total iron. It's quite important to look at the organic carbon, dissolved oxygen, those sorts of water quality parameters. How much iron is too much iron in a bore? That's always a good question. I've seen iron precipitation occur where concentrations have been in the order of 2 milligrams total iron per litre. I've seen other cases where we haven't got iron precipitation and it's been as high as 5 or 6 milligrams per litre. Australian groundwaters are naturally rich in iron in a lot of places. You can get iron concentrations up around 12 to 15 milligrams per litre, total iron concentration. They do tend to cause problems, but it's very variable, and precipitation of iron there's no one rule that says we're not going to have an iron problem if the concentration in the groundwater and in our source water is less than 2 milligrams per litre. A lot of other factors come into play. Making sure that we don't introduce issues that are not likely to be prevalent. You can probably go through this list ideally, but if we look at one of the issues in terms of clogging, where we might have chemical interaction with the screen, the riser or the sampling device, we want to make sure that those materials don't contain things like lead or zinc. So therefore we want to make sure that we're using inert materials. Chemical consequences, I'm just looking at this sort of green highlighted line here, may result in high concentrations. On recovery, if we've got reactions occurring because of the material constituents in the pipelines and materials and valving that we've used in the system, that may make the water unsuitable for its intended end use. So we need to make sure that we don't have those sorts of possible contamination sites, I guess, for one of we can call them, that may impact on the recovered water quality. They can also result in those food sources for various microorganisms. Iron-3 reactions, they can occur very fast and clogging can occur very quickly. Manganese precipitation typically occurs much slower. Both of them can be accelerated by microbiological activity and where we have an oxygen reducing environment. Water in contact with a mineral phase basically tends towards equilibrium with that mineral. And again, this is where we look at our hydrogeochemical modelling between our source water and our receiving water, and also understanding our aquifer matrix. Now, some of the hydrogeochemical modelling software, FreakQC, Mintech, Aquachem, Geochemist Workbench, PHT3D, all suitable modelling packages that can look at those geochemical reactions that may occur between the source and receiving groundwater. This is looking at just how do we assess the fate of iron in from an oxygen-rich store water into an oxic-confined limestone aquifer. The source water is oxidised and reduced iron, goethite, hematite, pyrite, certainly confirmed within the aquifer mineralogy. The native groundwater iron total was about 1.6 milligrams per litre. The source water iron total had a median of about 0.45 milligrams per litre. The recovered water iron basically ended up with a median of around 0.36 milligrams per litre. And the increase in iron was predominantly due to the release of dissolution and oxidation of pyrite within the aquifer. So that was the outcomes of our geochemical evaluation, looking at those different source and receiving water iron concentrations, and therefore we've determined that we're going to potentially have an iron problem, which could result in sulfate reducing bacteria or the development of iron flock within the borehole, which would ultimately lead to clogging if it wasn't managed effectively. This just gives a decision tree to identify the potential for iron mobilisation. So you can work through this decision tree and work out whether or not you'll come down have issues with dissolution of iron oxide or increased iron in the recovered water that may need treatment. One of the byproducts could potentially, if you've got a lot of pyrite in your groundwater system, could be arsenic, which would impact on the quality of the recovery water and what you can actually use that water for in the end once it's recovered. It's just a simple thought process that you can go through and then work out whether or not you need to do any further detailed geochemical modelling, potential characterisation of the source waters, and leads to decisions in terms of how you might want to treat the water prior to injection. Recharge bore design and construction. Again, thinking about how we construct the bore has implications for how we're going to operate the scheme, and also how we might mitigate any clogging that has occurred during operation. So if we've got a screened bore, it limits the opportunities for remediation, and also it can limit the injection efficiencies within a bore, because obviously once you've got a screen in place, it will start to increase the natural well losses. So therefore, the rates at which we can inject may be reduced. So we want to design our bores to make sure we can have as many options available to us to remediate the bores in the event of clogging. Now we've got to remember that the bores used in Manichac for recharge, or ASR, where we're using the same bore for injection and recovery, they're not simple water supply bores. A little bit more care and attention is needed when we actually construct them. Unlike conventional water supply bores, re-injection bores may actually have to withstand considerable operating pressures. So we've got to then consider what sort of materials we're going to use, how we're going to grout and cement the casing in place. We need to consider the drilling methods and drilling fluids. If we're drilling with mud, are we going to introduce a whole bunch of, are we going to have problems with the mud recovery and cleaning it out? What are the pressures that we're going to be using during injection? Leads to selection of materials that we might use. What's our screened interval or our production zone? What's our design going to look like to remediate clogging should it occur? We need to consider bore conditioning and development ahead of any recharge that might occur, ahead of any shut-in periods where the scheme might be idle for a period of time, and then again bore conditioning and redevelopment ahead of any re-injection after a period of time where the bore's been shut in. Pump hydraulics, we're going to consider the size of the bore. Larger diameter bores allow larger pumps to be inserted when we need to backwash at higher rates than what we might inject and recover at. We can maximise our bore efficiencies through correct development to allow bidirectional flow through a gravel pack. We can prevent cascading of water into the well so that we're not aerating the water as it goes into the well bore and introducing a lot of oxygen. We can make sure that we remove all the drilling fluids, correct management of drilling mud weights, drilling viscosity throughout the process, and bore conditioning during drilling, which may mean dumping a whole tank load of mud and putting in fresh mud to recondition the bore before we actually run casing, can actually help to improve development of the well on completion. We want to make sure we select the correct materials, casing, pumps and other downhole equipment. Access to the bore is appropriate for rehabilitation. There's always a challenge at the end to manage access if we need rehabilitation to be done, in that if we don't encase the bores, that they're open to vandalism and theft. Whereas if we enclose the bores in screens, fenced or sheds or something like that, makes it very difficult to then get a drill rig back in or appropriate equipment back in to actually remediate the bores. So there's some of the considerations that we need to think about when we're siting our bores and drilling them. Drilling methods, lots of different ones. Cable tool, not so much these days. Where you've got loose unconsolidated sediments, it may be the only method, but things like sonic and acoustic drilling certainly replaced cable tool drilling. There's auger, rotary mud drilling, air hammer, reverse circulation. Each has its own advantages and disadvantages when we're constructing a well, but we've used all methods in constructing ASR bores or managed aquifer recharge bores. We want to control the drilling process, proper mud control. We want to use experienced drillers that are familiar with the ASR systems or have drilled ASR bores before, or we want to sit down with our drillers and make sure they understand the objective of the bore, and that it's not just a simple production bore. It needs to both inject and extract groundwater, which means a slightly different construction. And we want to make sure there's proper development on completion of the bore, which means enough airlifting and enough development that's not going to actually create additional issues in the longer term or leave residual muds or other drilling fluids down the hole. And we get rid of muds, etc., using revert chemicals that help break down the muds, and they can be developed and gotten rid of. Types of completion: open hole, great where you've got a competent formation and it'll stand open, and that leads to lots of different methods for bore remediation. Natural gravel pack is probably the next best method, whereby you put in a telescopic screen and then just let the formation fall back against the screen. Gravel packs and screens, probably my least favourite method, but in some formations it's totally unavoidable and it's required. One of the things we need to think about when we're putting in a gravel pack is that we want to put in washed gravel. Quite often, if we just use gravel from a local supplier and it comes in bags, it often has a lot of fines material associated with it. So we put the gravel pack into the hole, and we've also put all of these fines in the hole as well when we're installing the gravel pack, and we've just created a clogging issue through the installation of the gravel pack. So just a bit of care needs to be taken if we are using a gravel pack. Screens and gravel packs also limit the options for bore remediation, as I said. They also limit the options of how you may, in terms of your injection pressures and injection rates that you may be able to achieve. You can just give an example of the hydraulic effects of the different methods. Open hole, significantly less well losses involved. Once we get up to a screened and gravel pack well, that can add sort of 7 or 8 meters worth of head during injection, or 7 or 8 meters worth of extra water pressure during injection, simply through trying to force water through the screen and gravel pack. So they do influence the well loss and also the remediation options. Construction materials, ideally it wants to be inert, typically PVC, fiberglass reinforced plastic or stainless steel. Just bear in mind that if we're using stainless steel in a anaerobic situation where we might get sulfate reducing bacteria, hydrogen sulfide gas can react with stainless steel, causing pitting and corrosion or increasing the corrosion. We don't use mild steel casing if we can avoid it, because the zone of the active zone across the wellbore, whereby it might be exposed to oxygen due to drawdowns during pumping and during recovery, and I suppose impressed or injection heads during injection, that zone is quite active, and over a 30-40 meter length of steel that gets oxygenated, that just sets up opportunities for corrosion. Things like rust and other things can start to occur over a period of time, and will ultimately lead to clogging over time. Generally in screened wells, clogging occurs close to the screen or in the gravel pack. Therefore, rehabilitation is often needed more frequently, or due either to chemical precipitation, microbiological growth, or accumulation of particulates from the recharge water. So therefore, our remediation strategies or operational strategies may necessitate significantly more frequent backwash events, possibly even daily. A backwash event may be required to maintain our injection efficiency and prevent clogging. If we've got an open hole completion, it's really important to make sure that we develop the bore up well, that we get rid of all of the fine sands. We're not continually producing sands, especially where we might get issues of dissolution. Conventional airlift development first, airlift, and there's often a question I get is that if we're doing an airlift development, aren't we just simply introducing oxygenated water into our groundwater system and oxygenating that near wellbore zone because we're forcing air down to the hole and then developing it? What we've got to think about is the process of that air development. Is that it's a surging process, so it surges and displaces water out of the bore using air, and then basically there's another inrush of water from the formation that will bring any entrained air with it and discharge it. However, there's often some small air that is trapped behind, so it's absolutely important that a pumping test is conducted as soon after the well is developed as possible. So if we do these aquifer discharge pumping tests and we run it for a 24-hour period or something like that, and we measure those parameters of pH, redox, dissolved oxygen while we're doing the pumping test, that will give us a good indication of when we've got equilibration and native groundwater being produced, and we've got rid of most of the oxygen, and therefore we can reliably determine that yes, we don't have highly oxygenated water left in the aquifer as a result of the airlift development process. If the well is going to be shut in for any period of time following that pumping test, it's best to treat it using an appropriate biocide. There's lots of them done. If there is a real concern about the introduction of oxygen and about the oxygenating the groundwater system, then we can develop the bore following completion using a vacuum approach. Just almost a Venturi system, which creates a vacuum and can clean out all of the fines material. If we're just using a natural formation pack and a telescopic screen, we can use conventional well development, airlift after adding the mud revert, followed by pumping development. We can use injection recovery slugs for screened and gravel pack bores, which means cycling fresh water and recovering that fresh water over a period of time, and it's a stepwise development, incremental volumes of fresher water and incremental volumes of incremental rates of injection and recovery, so that we're basically using almost an injection / recovery process to develop the bore. So it's sort of cyclic development of the bore to make sure that we get that bi-directional flow through the screen and the gravel pack. Again, surge block development is another way of developing a bore. If it's used, it really should be followed with a pumping test and pump development to make sure that all of the air is out of the system. So during operations, how do we identify and manage clogging? We can manage clogging in injection bores, and the reason we do this, we need to consider that it does result in extra operational and maintenance costs. and we want to make sure that we don't have to replace any of the injection bores. And if it's not recognised in time, it'll certainly cause loss of production capacity and lost harvesting opportunities, especially if your source water is stormwater. We can manage clogging through engineering design, chemical intervention, operational practices, and importantly, monitoring the scheme performance. We need to consider sediment loadings, heavy metals, pH, our total organic carbon, in short, our source water quality and our receiving groundwater quality. How do we recognise clogging? Basically, the hydraulic response in the injection bore is the best way to recognise clogging. This just gives some examples. Over a short time, a rapid head build-up in the injection well might be indicative of gas entrainment. Over time, we might see a gradual change within suddenly an exponential rise in injection heads for the same injection rate, which might be indicative of microbiological clogging, where there's an abundant food supply. We might see this tapered effect where there's a limited food supply and some initial microbiological activity, and then it drops off after a period. Suspended solids, typically gradual build up in head over time for the same injection rate. To assess this, we want to make sure that we've got the appropriate inline monitoring. So we want to look at the pressure in the injection bore. We want to have monitoring in the monitoring probes, pressure transducers in the surrounding bores we're using for monitoring, inline instrumentation to monitor turbidity, pH, temperature, electrical conductivity of the source water, and sometimes dissolved oxygen. However, we've found over time with dissolved oxygen probes, they foul very frequently, they cause issues, they make off readings, and the system is often down more than a knot if you're using dissolved oxygen as an indicator. So we've sort of dispensed with using the DO probes in line because of the problems that they've caused over time. And generally it's turbidity, pH and temperature that are the key things that we need to look at in line in terms of our source water quality. Just a quick case study looking at well screen clogging over successive injection cycles. Specific capacity is a great indicator of whether a screen is clogging due to chemical or mechanical issues. Screen clogging is basically characterised by the increasing resistance or increasing head over time for a continuous or a constant injection rate. Sort of wellbore clogging is basically characterised by the entrance resistance that increases slowly over time. So that's the little examples I gave in the slide previously, looking at injection heads over time for the different types of clogging. Specific capacity is one of the calculations that's used to check the bore performance during recharge and to check the effectiveness of any remediation on a clogged bore. Now it's really important to calculate specific capacity at the same time step and at the same injection rate, otherwise you can't compare. So if you're looking at comparing an injection, the specific capacity for an injection rate of 20 litres a second, it should always be done at 20 litres a second, and it should always, and the time step might be after the first 50 minutes of injection or after the first 100 minutes of injection, but that time step should always be constant, and it should always be the same. Otherwise you can't compare apples with apples. So this is just looking at the injection heads in the well over time on successive injection cycles, and then we can, what we would normally expect to see is a straight line shown by this dashed line over time. Any deviation from that straight line on a log linear cycle is indicative of clogging. And basically here we can see the deviation occurring after about 1,000 minutes worth of injection, suggesting that we've got clogging occurring. And I think I'm probably starting to run out of time, so I will skip through, I will move through the questions fairly quickly, or the remainder of the slides fairly quickly, so we can get to questions. This is an example of our looking at the specific capacity and time in that same injection bore. We've got a baseline and specific capacity calculated during the step drawdown test. This was our specific capacity during cycle 1, 2.1 slight improvement. Second, 2.2, we had a drop off, rehabilitated the bore, we've got a recovery, but over these successive cycles down to 310, we've had another drop off, indicating that we do need to again do some remediation and backwashing of that bore. You can also look at the chemistry of the recovered water to determine whether or not there's a clogging issue. Typically, elevated iron hydroxide is the thing that we're looking for in the recovered water, if it's significantly different over time. Control of air entrainment. The only way we can do that is with a downhole flow control valve. They're typically installed where we have a significant depth to our standing water level in the bore, or we are injecting at really, really high rates, because the high rates enable us to use both the rising main and the well bore annulus to inject those volumes. Or if we have a limited internal diameter is where we might use a downhole flow control valve. The rough rule of thumb is if the standing water level is sort of greater than 20 to 30 metres below the top of the casing, you may need to consider the use of a downhole flow control valve to prevent that water cascading in the bores. Our remediation, we've got mechanical techniques, physical techniques, and the chemical techniques. So mechanical techniques may include backflushing, and the frequency of backflushing is really dependent on the source water quality and bore construction. It can be daily, weekly, or maybe even once a year. We can use intermittent pumping, surging methods, or vacuum methods, or if there's in an open hole situation, reaming is another, under reaming is another method to actually manage the injection. Pumping up and down of ramping up and down of submersible pumps can also help, but that's fairly hard on equipment. Physical techniques, we can pasteurize our water, disruption of chemical and microbiological processes by freezing and pumping. I've only ever heard of that being done in one place in Europe. It's not typical. Chemical techniques, chlorine, acidization, and other methods are other issues that we need to look at. Right, just having a quick look at my phone because we are getting a number of questions coming through, which is great. So do keep those questions coming, especially if I'm talking a little bit too quickly and I've skipped over something. Water treatment options to mitigate clogging in bores: strainers, filtration, micro or ultrafiltration are typical mechanical methods that we can use. Disinfection, we can apply chlorine, chloramine, ozone treatment, or additional UV treatment to manage microbiological activity. pH buffering is another mechanism to manage the risk of chemical precipitation. So all of these engineering solutions can actually be added onto the system design. Some additional filter options. If there's a lot of organic carbon in the source water, we can use activated charcoal. Activated carbon can also be used to manage emerging pollutants in source water, such as PFAS. However, the activated carbon needs to be reconditioned periodically, and if there are things like PFAS in the water, it's sometimes difficult to dispose and recondition the activated carbon. I think I've mentioned a couple of times throughout the presentation that we need to consider bore conditioning, and that conditioning involves making sure that when we first start up the scheme, that the pipeline supplying to the bore headworks is fully charged and free of any air before we inject into the wellbore. It may mean running a downhole closed circuit television to ensure the screens are free of any debris or any other material and that the development is correct. We can do a conventional well development first, a bit of purging or pumping to make sure that if the bore has been idle or stagnant for a period of time, that any of that stagnant water is discharged to waste before we start injecting. We might consider doing some cyclic conditioning prior to recharge commencing, just small volumes, low rates, inject, extract, and incrementally increase those, which is what cyclic conditioning is. And if we do use cyclic conditioning, it should be over a period of 2 to 3 days. Some of our operational measures to mitigate against clogging: flush all the wellhead and piping prior to any recharge, especially at the beginning of recovery and for a few minutes, and that can be for just a few minutes or an hour. Periodically backflush the well. Again, what we've found over time is that prolonged backflushing at a single rate doesn't really do much. Most of the backflushing occurs in the first 15 minutes, and so that's really as you know, between 15 to 20 minutes is about as long as you need to run a backflush event to remove any accumulated solids or biomass. Our typical backflush frequency is every few weeks to a month, but we have been operating a scheme where backflushing is required every day. But again, it's only for 15 minutes a day. The same pump installed in the bore can be used for backflush and recovery. We can use the radial injection surge development method, which was a method developed by Tom Morris when he was at ASR Systems in the US. That's a very effective means for developing clogged bores. How do we control some of that microbiological activity? Chlorination or UV of the source water before it goes in. Ozonation is another method that can be actually treated, but that's increasing the infrastructure costs. A number of our schemes have UV treatment on them where they don't have sufficient residence time through a wetland, which applies all of that passive treatment. Wetlands, you probably need, if you're looking at those as a passive treatment mechanism, need probably 8 days residence time of the water flowing through the wetland to achieve the 2 log removals of microbiological activity. If the water is to be supplied for a drinking supply, then you'll probably need to attain a 6 log removal. That can't be achieved by chlorination alone. So you may end up having to use a combination of treatments such as chlorination and UV treatment or microfiltration if the water is for a drinking water supply. Remediation methods such as acidization. We've achieved a couple of, we've done sort of about 5 or 6 bores that have required acidization to remediate clogging. Generally, it's a kind of a last step resource, but because the aquifer was a carbonate aquifer, it was favourable, the conditions were favourable to use hydrochloric acid. Basically, in a carbonate aquifer, it results in the production of CO2 and water, so there's no residual hydrochloric acid. Some of the literature suggests using hydrofluoric acid. However, I would caution using that because it's really, really high risk. It's extremely corrosive. There's issues with transporting such a corrosive acid to site, so probably not recommended in most situations. This gives a little bit of an example of chemical treatment and vacuuming to remediate microbiological clogging. In this sort of upper little picture, we can see this black sludge around the wellbore, which is indicative of sulfate reducing bacteria. That's sort of a black slime that it produces. On the fiberglass reinforced plastic rising main, we've got this sort of black scale, blacky browny scale that's developed in this mid photo. After we did the chemical dosing, this was a greeny black sludge that we actually produced from within the bore itself. And once we used the sulfamic acid, a mixture of sulfamic acid, liquid chlorine, dry shock chlorine, and salt to rebalance and re-equilibrate the system, because it resulted in a fairly low pH with the sulfamic acid. That's what we ended up with, was that sort of greeny black sludge. We did a jetting and brushing of the bore. We repeated that chemical dosing and then did the vacuum suction and cleaning to remove any residual debris from around the production zone. Reinstalled the pump, scoured and surged, and then repeated the step drawdown testing to confirm that the rehabilitation approach was effective and efficient. Some of the lessons learned over sort of 20 years of managed aquifer recharge into bores. Clogging will happen, but it can be managed. To recognise the potential for clogging and to mitigate, we either do that through engineering design or through operational management practices. And that's really why we do need to understand the risk of clogging up front and consider that in all aspects of our design and through the investigation stages of our managed aquifer recharge scheme, so that we know whether or not we're going to have to install additional treatment above ground on our source water, or whether or not we can successfully manage the clogging potential through just operational practices. Hydraulic performance of the injection bore is one of the keys to assessing ongoing clogging during operations. Knowledge and skills are required to remediate clogging, getting contractors that have the right sort of equipment and are familiar with treating bores. The treatment chemicals that are used are quite common for treating production water supply wells, so that there's nothing new. They're generally accepted by regulating authorities such as the EPA, so there's no lasting environmental harm in using these chemicals that we use for remediation. Characterising our source water and receiving water is absolutely vital to working out, do we have a clogging risk? The remediation methods to address clogging are very site specific. What may work in one well on the site may not work on the next well at the same site. And the methods applied in one location may not be applied, may not be successful in another location, because factors like pH and our water chemistry and temperatures and things like that all come into play in terms of what the clogging causes may be, and what the remediation, and therefore what the remediation methods might need to be in terms to mitigate the clogging. One of the things that we want to do is make sure we identify and prioritise the objectives for each MAR system, because that will determine how we manage clogging. For example, if it is a potable water supply and the demand is going to be constant and there's not a lot of opportunities for downtime to remediate the bores, then we need to think about how we design our systems. We might need to have a level of redundancy in the system such that if one bore is offline being remediated due to clogging, we can still meet any supply demands that we may have. It may mean that if we're looking at a potable water supply, the level of pre-treatment will obviously need to be much greater, and therefore the investment in the capital investment in pre-treatment needs to be a lot higher. part of our process that we go through when after we've done the initial field investigations is we do look at a risk assessment that considers the potential for clogging, and then we construct our investigations around the risk and potential for clogging and what we need to do and what sort of information we need to collect during those preliminary field investigations. We basically source and receiving water quality, understanding our aquifer matrix. We can use things like laboratory studies, column studies, etc. to help us understand that risk of clogging, and we can have a planned cycle testing program that'll help us understand that risk of clogging. The main causes of clogging in ASR bores or managed aquifer recharge bores is poor well construction, poor characterisation of the source and receiving waters, poor characterisation of the aquifer mineralogy, and poor well design. Often there's inadequate development post completion, and then failure to adequately condition the bores prior to commencing recharge after a period of shut-in where the bore's been idle. Often everybody just turns around and says, oh, the system's all connected together, it's just a matter of turning on the pump and allowing and then starting injection. But quite often it's best to actually start pumping the bore before you do any re-injection, and making sure that it's properly conditioned and the system is properly conditioned, so that you're not introducing bacteria or other materials that may have grown in the system while it's been idle. Some of the engineering considerations: we can use filtration, simple sand filters to membrane filters, activated charcoal, UV treatment and chlorination. Downhole flow control valves, where we have significant depths to water and large volumes required to be recharged. Addition of chemical processes to buffer and balance pH. Just a reminder that the ASR bore is not a simple production bore. We need to make sure that the material selection we used in construction is appropriate. The drilling method to construct the bores is appropriate. We've got proper completion and we've got proper development of the bore. Make sure we collect those baseline aquifer parameters, that step drawdown test, do the specific capacity, and that should be determined on all production bores. Constant rate discharge tests, maybe 20% or 30% of a well field, that should be completed. Consider the completion options for the possible remediation strategies in the event of clogging. So open hole, natural formation pack, or screen and gravel pack. Remediating a screen and gravel pack is obviously more costly than remediating an open hole when we're looking at managing clogging. During operations, consider backwashing cycles. How frequent do they need to be? Periods of dosing. You may not need to install constant chlorination to manage the risk of clogging and manage any microbiological activity. So it might be that periodic shock dosing of the bore every 3 to 6 months will be sufficient to actually control any microbiological activity, rather than investing in chlorination units. We want to make sure that we condition the bore, treat prior to any shut-in periods, which means dosing with an approved biocide chemical, purge all bores prior to recharge events, and make sure that pipeline to the injection bore is completely purged and charged of any completely purged of any air and stagnant water prior to injection. And that's me finished. So if I can switch off my screen and stop sharing, we can probably take some of those questions.
Thank you so much, Martin. An excellent presentation. And if you agree, we are going to answer the questions. Are you agree?
Yeah. So okay. If the questions have come through in Spanish, you translate them for me, or if you want to run through them.
No, fortunately, they are in English.
Good.
So I think that the first two questions, we can put it together. It's coming from Leo Amores. How often do wells near to the beach require maintenance? And in your experience, do you recommend wells near to the beach?
It depends on what the purpose of the well is. If we're looking at managing seawater intrusion, and we've created, we're using managed aquifer recharge to create a hydraulic barrier to prevent seawater intrusion, then the closer to the beach, I guess, is better, because we can really, create that barrier and prevent the seawater intrusion. Now, again, in terms of maintenance and management, obviously being near the sea, the headworks and the infrastructure is going to be subjected to corrosion. So you can use materials like casing materials like PVC, or above ground pipe work like high density plastic piping to give the rigidity and structure to withstand the pressures to use. That'll all improve the longevity of the casings close to the exposed infrastructure close to the coast. But generally, we've put PVC bores in really saline aquifers where the groundwater salinity is in excess of 40 or 50,000 milligrams per litre, and those inert materials like PVC or fiberglass reinforced plastic are ideal for those sorts of conditions. Stainless steel, so long as it is 316 or higher quality stainless steel, is also suitable, but it's also much more expensive than PVC, and the cost of stainless steel versus the cost of PVC probably needs to be weighed up. Equally, they have a similar lifespan of 30 to 50 years, I guess, in those sort of harsh environments. We've had wells in the Great Artesian Basin, fiberglass reinforced plastic, that were installed in the 1980s, and they're subjected to high salinity and high temperature. Groundwater temperature is about 120 degrees C, and so they've withstood those fairly aggressive conditions. So
thanks.
Hopefully that answers the question.
Yes, really good. Thank you so much. I have another questions. I knew that the bacteriological process associated with the precipitation of sulfide occur at high temperature. In the case of groundwater, do these biochemical process take place?
They do. Certainly sulfate reducing bacteria, if it has a food source, generally sulfur or organic carbon, and any other sulfides, they will start to create those, that provides an ideal environment for bacteriological activity to I suppose, develop, and the sulfate reducing bacteria are, I suppose, natural organisms that live in groundwater. They're natural organisms and iron bacteria. So the condition, if they have favourable conditions, they can be quite aggressive, and populations grow quite rapidly.
So, are the same techniques applied to prevent clogging? No, I think that is clogging.
Plugging,
are the same techniques
plugging.
to prevent clogging at any depth?
Pretty much. Any of those methods can be used at any depth of well bore. Obviously, the deeper the bore, if we're looking at significant chemical treatment, and we're just in the process of doing a major redevelopment of one bore that's about 330 metres deep. So the deeper the bore, unfortunately, the greater the cost in terms of remediation and time taken to get the equipment over the bore, get down to the target depth where the screen is at 320 metres, and then start to do the remediation and development. And of course, these are large diameter bores of 15 or 16 inch, so they the volume within the bore itself, the standing water level is 10 metres below ground, so we've got a water column of about 300 metres. So there's a lot of natural groundwater and bore volume within the cased bore itself that we need to overcome and make sure our chemical dosing and chemical concentrations are correct to achieve the method. So shallow bores, cheap, quick and effective, but yeah, all of the methods are appropriate for cleaning a bore of any depth.
Thank you, Martin. Another question. Have there been cases where clogging is impossible to treat?
I haven't come across one yet. I've had some pretty challenging ones, but yeah, so far we haven't had to walk away from any of the bores that we've installed, and some of these schemes have been operational now for over 20 years, 25 years. Some of these schemes have been operational, and they've only required one remediation event. I do know, talking to other colleagues, that some bores have, due to the inexperience perhaps of the people that were investigating the scheme, they walked away from it. We finished one scheme, and it was actually for re-injection for vegetation health, for vegetation maintenance in that highly saline aquifer I used through the example. There were two previous attempts at doing managed aquifer recharge that had failed due to clogging. We were the third attempt, and we had a shoestring budget and very little confidence of the proponent that we would have any sort of success. We did have a couple of clogging events during the trial. It was a 8-month trial, and we basically successfully remediated the bore. One clogging event was due to silt, and the other clogging event was due to algae in the source water. And both times we successfully remediated the bore and developed a freshwater lens of less than 500 or 250 milligrams per litre in that 35,000 milligram per litre saline groundwater system, and that was to sustain. It'll be the topic of an upcoming paper at ISMA next year.
Wow, really interesting. So another question. Is there some kind of study or assessment that relates economical losses in MAR projects for clogging?
So economical losses in MAR projects for clogging. No, that's probably a gap that hasn't been addressed yet, and it's particularly relevant where a lot of the schemes we have probably, I think we've got 120 recharge bores in South Australia across 20 different schemes, and the source water is predominantly stormwater. And where we get clogging, it results in lost harvesting opportunities, and that water is captured during winter and then sent for irrigation during summer, but sometimes the bores are clogged and they require remediation, and therefore that harvesting opportunity is lost because stormwater is a little bit intermittent. But that study actually hasn't been done, so it is a gap looking at the lost economic opportunities associated with clogging and remediation if you're not I suppose on top of it and managing it. And that microbiological clogging sulfate reducing bacteria, the series of 3 slides, that system was non-operational for an entire year. By the time they lost the opportunity to harvest stormwater during the winter, and then all of the remediation occurred during the summer months, so they couldn't supply their customers. And it's off the top of my head, it's a 20 million litre scheme, and the cost they receive from customers is 60 cents per litre. So that might give you a bit of an indication how much money they lost during a year in terms of revenues from that scheme not being operational.
Okay, thank you. Good numbers. We need to make the calculation.
Yeah,
so,
I put off my head, but I can't.
To divide. So another question. In fractured rocks, what are your experience regarding clogging?
Yep. At least 6 of the schemes we operate here in Adelaide are in fractured rock, and all of the schemes that I've been involved on in Western Australia, in the northern part of Western Australia, are all fractured rock aquifer schemes. Again, aquifer characterisation is key to understanding the fracture orientation and direction. So using downhole tools, in particular the acoustic televiewer, that enables you to get an indication of fracture orientation, dip and strike, is absolutely critical in understanding and characterising that aquifer heterogeneity. In some cases, if you're injecting large volumes, and again, you need to use your groundwater numerical modelling to help with this, we've found that the injected water very quickly moves beyond the capture zone of a particular well for a given pumping rate. So it may be appropriate to install wells along the hydraulic flow path and then almost operate the system as an ASTR. So you inject in one well and then you have another well along the flow path or fracture orientation and recover simultaneously from your production well and your well down gradient to make sure that you're maximising your recovery efficiency. But by and large, the fractured rock systems are more favourable because you can inject at much higher rates, but because you are limited to a fracture network, the fractures can clog very easily. But again, the fractured rocks are competent, so you can construct with open hole. So the remediation methods that we've used in the past are potentially a little bit of under reaming, just to skim the sides of the borehole and free up any clog material and make sure that we've got fresh open fractures to inject into. But by and large, we've found by managing the source water quality and managing our turbidity to less than sort of 2 turbidity units or suspended solids of less than 2 milligrams per litre, that is really the key to managing fractured rock aquifer systems.
Thank you, Martin. I think that this is our last question. Not being expert in the area, I get the perspective that the clogging process are mainly chemical, driven instead of hydraulic driven. Is that correct supposition?
It can be. Most of the clogging that we've experienced and most of the remediation is both either chemical or microbiological. The schemes that have been operating for the longest have typically been microbiological activity due to perhaps those poor practices of not conditioning the wells prior to injection. The chemical clogging processes we've typically been able to manage and control through controlling things like aeration and pH buffering and injection rates and making sure that we're not and controlling the oxygenation of the source water. So we've been able to limit those chemical reactions. So yeah, characterising the aquifer and characterising the source water are the key to preventing those chemical precipitation reactions occurring. But yeah, they're probably the two main chemical and microbiological are the most common ones that occur. Oxygenation facilitates chemical precipitation. So we did, again, we had one project where there was suddenly a whole bunch of air entrainment occurring, and we were getting air clogging where we hadn't experienced it before. The scheme had been operational for 6 or 7 years. And basically what they'd done is they'd installed a balancing storage tank midway through the supply pipeline, and they were allowing the source water to cascade into the balancing storage tank. So they were aerating that source water, and then it was being transferred to the ASR bores. The oxygenated water precipitated or led to ion precipitation, which led to an increase in sulfate reducing bacteria. So when we did our initial analysis, we found elevated levels of sulfate reducing bacteria and slightly elevated levels of iron being the problem. So we naturally assumed that the problem was available iron and sulfate reducing bacteria. Treated and reconditioned the well for the iron bacteria using a chemical treatment process and backwashing, only to have the same problem occur again in 12 months. So once we finally sorted out what had happened and why we suddenly were getting this issue with iron precipitation and iron bacteria, and we looked at whether or not there had been any system changes downstream of the bore headworks, discovered that that's what they'd done. They'd introduced this tank and hadn't told us about it. And so once we solved the cascading issue, which was simply lowering the pipe to the bottom of the buffering storage tank, our oxygenation problem went away, our iron precipitation problem went away, and so did our iron bacteria problem. So it's a little
complicated.
A little bit complicated. So yeah, it's understanding those interrelationships between the different potential clogging mechanisms.
Yeah, thank you, Martin. I'm just going to ask you the last question. I want to know your opinion. What do you think about to use abandoned wells or old water supplies wells to make recharge? Is just trying to reuse these old wells or drilled wells and use them to make recharge.
Yep. If we have to go and again, I saw a classic example of this in Queensland, where somebody used an old recharge well, thinking, yeah, we can just do that, and they jumped straight in and did the recharge. They didn't look at what the condition of that well was. It was an old steel constructed well, so they didn't look at the condition of the well to start off with and look at its construction details. So In that particular instance, if I was I got called in afterwards to clean up to fix up the clogging event. What had happened was that they had just done an injection of, unfortunately, it was RO'd water. So it had a really, really low pH and it was really, really aggressive, and it just stripped all of the rust and everything like that off the inside of the casing, and the bore clogged. So in that particular instance, one, I would have looked at the source water quality and gone, it's RO water, so therefore it will need some buffering, either mixing with some other source water to bring that pH back up, and would have run a CCTV camera to understand what are the issues and what is the condition of the casing in the borehole to begin with. And then basically recondition that borehole, put a pump in, put a scrub in, depending on what the downhole camera tells me. Then you would look at conditioning that bore prior to actually using it. Conditioning, if it's got a lot of rust and scale involved, you can put scale inhibitors in as part of the conditioning process. Treat and brush and clean out all of the old material so that you've almost got a clean, fresh face to work with, and then go forward from there, from the ASR board. So, you know, the cost of doing all of that might be, I don't know, 15, perhaps 20,000 US dollars maybe, versus drilling a new bore, which might cost 100,000 US dollars or more, depending on how deep you have to go. We've drilled some deep bores and they've been 500,000. So.
Yes, good comparison. Well, thank you so much, Martin. We are really happy that you share your experience with us. As always, you are really, you share and you take the time to share with all your experience and knowledge. We are really happy to have you here. So I think that is all, and thank you so much again.
Yeah. Appreciate that, Adriana, and I'll provide you a copy PDF of the slides so that you know, for participants and others, quite happy to share the slides and everything like that, because some of the things I did go over fairly quickly. There's a little bit more information and detail in there, so if the participants want to contact you directly, Adriana, you can just send out a copy of the slide PDF.
Thank you so much. We are going to post in the YouTube channel the link to download the presentation, and of course, we can make an email to us to receive this information. Thank you so much, Martin, and I think that Fernanda is going to say goodbye. Thank you.
Thanks, Adriana.